With that, I'll keep it short and welcome Lynn.
Thank you for that. That was great, Bob. You know, nobody wants to listen to my checkered employment history, so I think that's great. And thanks for all your effort over the years and for the Krell Institute's commitment to science and math and technology-based education. It is a real contribution to the strength of this nation. And of course, I'm glad to be here this morning. My troops in the office know that I'd rather go hang out with students than almost any of the other assignments I have. So I'm really glad to be with you today. And of course, thinking about talking here made me remember back to my days as a graduate student at the University of Minnesota. So in those days, we were busy thinking about the fluid mechanics questions that arise from free surface flows when you have a flow of a liquid surface with a curved surface and surface tension feeds back in to make some nice complicated boundary conditions. And the problems have the difficulty that you have to actually figure out the domain that you're solving the problem on as you solve the problem. Now, you have to remember that this was the days of IBM cards, and the memory in the computer was so small. It was a CDC Cyber 74. So my codes would only run at night. So the fact that I'm still married to the same woman is a miracle because there were some time challenges and all that. And the thing that's fun to think back on, I mean, as far as I know, I wrote the first finite element fluid mechanics code at the University of Minnesota, which is a powerhouse in that area now. But the problem I solved would not even qualify as a homework problem now. So there actually has been some progress in the field. After my PhD, I spent 30 years at Stanford University, really working on how complicated fluids flow in the rocks in the Earth's crust, partitioning amongst the phases that are present and reacting as they go. Applications to oil and gas recovery or contaminant transport in hydrologic systems or even these days in CO2 storage in the subsurface. And in some sense, those problems are a reasonable example of the kinds of things that we need to face today. That is, they're fundamentally multi-scale problems. The flows, many of the properties of the flows are controlled right down at the pore scale where the fluids interact with the surfaces, where the curved surfaces between the phases matter, and where intimate mixing and transport at the smallest level controls actually what happens. But the flows that we need to model, partly they're dominated by the extremes of permeability, whether they're fractures or high or barriers to flow, which vary at scales that are much bigger than the pore scale, but much smaller than the scale at which we need to solve the flow, which could be hundreds to thousands of meters. So things going on at multiple scales with mechanisms, some of which we can represent directly and some of which are inevitably going to be done at subgrid scale. If you think about those kinds of multi-scale problems, now they are everywhere in the science and engineering community. Whether it's the fundamentals of fusion to the electrochemistry of batteries or the innards of a nuclear power plant. Think about the range of physical phenomena that go together. As we think about how to attack those problems, one of the things that we're very much trying to do is to reduce the amount of sort of assumptions about subgrid scale phenomena, that is to represent those physical mechanisms more directly so that we really can look at these big scaling problems as in a fundamental way. And I think you'll see that theme echoes through lots of what we do. But this is a huge opportunity in the area of computational science. And I'm quite confident that all of you will contribute in very interesting ways to what goes forward. So use this fellowship as an opportunity to move the conversation forward, to help us lead the world in this important area. So I want to just talk a little bit about this question of high-performance computing and where we stand in the U.S. and where we hope to go. So 4 of the world's fastest 10 computers or supercomputers are located here in the U.S., 2 of which are in the top 5. And that's a direct result of U.S. government investments in supercomputing for science and national security that has been stewarded by the Department of Energy over the years, and particularly the Office of Science and the National Nuclear Security Administration. So we're proud of that progress, no question about that, but we shouldn't declare victory and go home. There is actually lots of competition in the world. Just recently, the Top 500 organization released a report stating that China now has has not only the world's fastest supercomputer and 2 of the top 10 fastest computers, but they're continuing to work hard in this area. Now, of course, this is not just about how fast the computers are. That might lead to bragging rights, but what we really want to do is to solve difficult, hard problems that really help us change the world around us. If I put on my energy hat for a moment, I would say that there is such a rich fabric of interesting problems that we can solve more quickly if we can compute our way through the world around us. Think about what could happen if, for example, I could say to all of you, gee, I want this battery to be able to shuttle lithium ions in quickly and use a high-performance catalyst so that we can do electrochemistry to make carbon-carbon chemical bonds, for example. You say, okay, great, and off you go and design me a catalyst to do what I need in my electrochemical factory. Right now, we can compute the performance of the catalyst if I tell you what it is, but we can't yet answer the reverse question, which is how do you do those materials by design? And that's a big, hard computational problem that will demand the highest performance computers and our ability to think about the problems as well. So it's not just speed, but it's also architecture, it's also software, it's also our ability to use these tools in new ways. In July of 2015, President Obama issued a new executive order to establish a new initiative dedicated exclusively to supercomputing research. So that's a step along this road. This was creating a National Strategic Computing Initiative, or NSCI, and the President's order outlined plans to create the world's first exascale computing system. And the goal is very much to keep the United States in a leadership position for high-performance computing research going forward. And so we have within the Department of Energy the Exascale Computing Initiative in the FY16 budget to accelerate the development and deployment of capable exascale computing systems. Now, of course, this doesn't happen instantly. You do some steps along the road. We're working on upgrades across the National Lab complex right now that will greatly improve our capabilities. There will be a 200 petaflop Summit machine at Oak Ridge that will be coming online, and a 150 petaflop Sierra machine at Livermore by mid-2018, and a planned 180 petaflop Aurora machine at Argonne in late 2018. So these upgrades will help us on the speed side, but we also have to work on the software and architecture and application side to make sure we can use these machines the way they were intended. And there are plenty of challenges in doing this. I just will note one energy scaling question here, and that is that if you just take the chips that we have now, basically, and say, well, okay, we'll get that speed by, just adding more processors to the system. By the time you get to the highest speeds, you need a small modular reactor sitting right next door to each one of those big computers. That's probably not going to be okay. So we really do have to work on the efficiency side of the most fundamental electronics as well. These machines will help us understand the fundamental physics, expand our knowledge of the universe, help us work on climate change, and think about the biomedical side as well. Now, you might not think that DOE is particularly well qualified to work on the biomedical side, and OMB definitely thinks that. But the truth is that there are now beginning to be ways that we can interact with that community in a productive way. So when the President announced in his State of the Union address earlier this year that Vice President Biden would lead a new cancer moonshot initiative, DOE was invited to be part of the team. And you might be asking, well, what can we do there? And it turns out that it's quite a lot. Just a couple of weeks ago, the White House held a Cancer Moonshot Summit at Howard University and announced a whole series of partnerships that are aimed at accelerating research and progress in cancer across that continuum. In partnership with the National Cancer Institute, DOE has announced 3 pilot projects that bring together nearly 100 cancer researchers and computer scientists and engineers to apply high-performance computing to the incredibly rich and varied data sets of things that range from genetic information to images to diagnoses to drugs to treatment in a way that will help us apply both machine learning and high-performance big data computing to a very complex set of diseases and problems that we can face. It will be set up with integration of big data analytics, data-driven modeling, and simulation with the Krell computer architecture. And then there's another partnership with the Department of Veterans Affairs. So we're joining forces to apply our computational assets to DOE's national labs to nearly 500,000 veterans records from one of the world's largest research cohorts, the Million Veterans Program. So the first phase of this project will also focus on cancer, cardiovascular disease, and mental health issues. And we're hopeful that this will accelerate our understanding of disease detection, progression, prevention, and treatment using the rich clinical, environmental, and genomic data that exist in those data sets. So the availability of high-performance computing, somewhat more capable than those powered by IBM cards, and high-speed networks, coupled with advances in algorithms and software and architecture in the machines, has the potential to create another revolution in the way we do our science and engineering across this country. So as you meet and talk to one another here today and over the next days, and over the years of your fellowship, share ideas, discuss, try to understand each other's problems. It turns out that no one of us gets to own our own chemistry and physics. We all get to work with the same fundamental pieces, and get to know each other. You will be surprised, I think, at how often your paths cross in unexpected ways and offer opportunities to work together on something that none of you foresee exactly right now. Take advantage of those connections. They can lead to wonderful things. And think about the role of science and engineering in our society today. We can all help us make progress. So you have a big opportunity. But there will also be challenges along the way. I'm thinking now about all my years of running a research group at the university, and then the excursion into administration as well. And writing code, but I eventually got to the point where the students were a heck of a lot better at that than I was. So I'll just make the point that having a very talented team is essential to a lot of what we do. That was certainly true in my research group. So for those of you that might end up as academics, or even those of you who will be research leaders in some other organization, I can reveal the secret of success. And the secret is that to surround yourselves with people who are smarter than you are. And I know this works because I made a whole career of it in an academic institution. And I have been, one of the blessings of my current job is that I get to look across the science and energy research spectrum at DOE, and there are so many talented people there that I'm confident that we can contribute in a big way in the future. And of course, that includes all of you. You are the kind of people that we need to lead us into the next generation of this kind of computing. And we thank you for that effort and for the work that you will do. So at this point, I will close and say thanks again for what you do and your efforts. In some sense, we're your team here, helping provide the resources and the tools and the machines that will make it possible to get to the next level. But none of that happens without the kind of work that all of you do. So for the organizers, the students, and the participants, thank you very much.